So far, we've been drawing force diagrams that may not be balanced if they have forces going off to angles. And if you recall from Newton's first law, objects at rest stay at rest, objects in motion stay in motion unless acted upon by an outside force. So if your objects are not accelerating, your forces need to be balanced. What that means is that in your force diagrams, your vertical forces need to be equal and your horizontal forces need to be equal. If you have a force that goes off at an angle, that's not the case. So what we have to do is break them apart into component forces. I want to start by reviewing what we already know from vectors. Any arbitrary vector that's pointing this way, or any way really, will have an x and a y component. And what that tells you is how far either to the left or right and how far either up or down that vector goes. So the way that you figure out how far to go is to look at the tip, and again, we've already done this with vectors, and figure out how far along the x-axis it reaches. So it goes about this far in the x, and how far in the y it reaches. It goes about that far in the y. So this becomes the x component, and this becomes the y component. So anytime we draw a force that's off to an angle, what you need to do is figure out those x and y components by looking at the tip and figuring out how far they go. So if this is any force, that becomes the x component of the force, and that becomes the y component of the force. And this is true if you're pointing in another direction. So say you were pointing down and to the left, the y component would go down. So this is a force. This is the y component of that force. I'm going to erase this. This is the force. And then this would be the x component, if I could draw this right. This would be the x component of the force. So let's see what this looks like on a force diagram. Say we have a force diagram, and this is going to be a box being pulled at an angle, and we'll say this is moving at constant speed. So the force diagram for this box, going down, we're going to have weight, Fg. Going up and to the right is the tension force. Going directly up is the normal force. And opposing the motion would be the frictional force. So since it's moving at constant speed, our forces need to be balanced. So what we need to do is get our vertical forces equal to each other and our horizontal forces equal to each other. So the force that needs to be broken up is this tension force right here, since that's at an angle. So the x component of the tension force, looking at the tip of the force, goes out to about, that's really not straight, goes out to about here, and we'll call that Ftx for being the x component of the tension force. And the y component is going to go up to about there, and that would be Fty. And by breaking this apart into Ftx and Fty, we cancel out that tension force. So I usually draw two lines just to show that it's canceled out. You don't want to completely exclude the tension force. You want to show that it is there at the angle, but once you break it apart into its components, it's okay to cross it out. So now in the x direction, I have a frictional force equal to the x component of the tension force. These two arrows should be equal in length. In the y direction, I have gravity going down. I've got a normal force and my y component of the tension force going up. Since it moves at constant speed, the length of this needs to be equal to the length of these two added together. And this is why it's really good to use pencils, especially with this. I'm going to make my Fg a little bit longer, if this will cooperate. So you want a pencil so that you can erase. And we're going to make Fg longer. to show that the length of this plus the length of this is equal to the length of this. You can eyeball it, you don't have to be exact, but you need to make it obvious that 2 added together will equal 1 long one. And this is how you would draw a force diagram broken up into its components. I'll do one more example, and then we're going to do a whole bunch of practice with this in class. So let's say now we've got a box being pushed down and at an angle, again moving at constant speed. So force diagram for this box, we've got gravity going down, we've got a contact force going down and to the right, we've got a frictional force opposing the direction of motion, and a normal force going straight up. This time the force I want to break apart is my contact force. It's the only one at an angle. So this would be FCX, X, and going down would be FCY. And that cancels that out. In the horizontal, my frictional force should equal FCX. In the vertical, FCY plus FG should equal FN. So now I have to make FN a little bit longer. To show that the length of this plus the length of this equals the length of this since it's moving at constant speed. So again, it's not terribly difficult to break these apart into components. I lied, I'm actually going to do one more example where they're on an angle. So let's do a box at rest on an incline. What you want to do here is use a dotted line to show your surface. Gravity points straight down, always. We've got the normal force perpendicular to the surface. Box wants to slide down the ramp, so we have a frictional force parallel to the surface. In this case, the vector that I want to break apart is the one that's not in line with the parallel or the perpendicular directions of the surface. So since normal force is perpendicular and frictional force is parallel, the force I want to break apart is Fg. So looking at the tip of Fg, this would be Fgy, because you want to make your surface your x. And this right here would be Fgx. Again, since the box is at rest, your horizontal forces need to be equal. So what I'm going to do is shorten the frictional force. Let's get this. So frictional force is now shorter, and then in the y direction, my normal force should be equal to Fgy. And doing that, breaking them apart into Fgx and Fgy cancels out my Fg. So anytime you're on any kind of angle, no matter what way the angle is going, your surface will be where your x-axis will be where the surface is, and you're going to want to break apart whatever's not in line with the horizontal or vertical axis. So anytime it's on an angle, usually what's not in line will be Fg. So Fg is only broken apart if you're on an angle. So this is how you break apart forces into their components. We're going to do a whole bunch of practice, and this is how you correctly draw force diagrams. So from now on, you don't want to leave them as we were leaving them with a force out to an angle. You want to break them apart and you want to make sure they're balanced. So if I ever say balance the force diagram, what I'm referring to is break it apart into components.